Hi, in this video, I will talk about the boiling point of organic compounds and the factors that affect the boiling point, and we will also define a couple of terms that are needed to understand the distillation process that is usually used in an organic chemistry lab. Vaporization versus condensation. Vaporization is the process by which a liquid is transformed into a gas upon heating. So whenever we have a compound that is in the liquid state, upon heating, if this compound is transformed into the gas state, the process is called vaporization. Condensation is the opposite process, and it is the process by which a gas is transformed back into a liquid, usually upon cooling. Now, both are considered as physical changes because they involve a change of state. Vaporization can occur either through evaporation or boiling. Now, what's the difference between evaporation and boiling? In evaporation, only surface molecules of the liquid will have enough energy in order to be able to break the intermolecular forces and escape from the liquid state into the gas state. So evaporation only takes place at the surface molecules, and those molecules which are in the inside of the liquid are not involved in the evaporation process. On the other hand, boiling is a process which involves the transformation or the change of state of all molecules of a liquid into the gas state. So in evaporation, only surface molecules are involved, whereas in boiling, the whole bulk of the liquid will be involved in this change of state process. And this is the main difference between evaporation and boiling. Evaporation can occur at any temperature. There is no need for heating, whereas boiling can only occur if the liquid was heated. Atmospheric pressure. What is the relationship between atmospheric pressure, vapor pressure, and boiling point? Atmospheric pressure is a downward pressure that is exerted by the gases of the atmosphere on objects at the surface of Earth. We all know that the atmosphere is of the Earth is filled with gases. These gases usually exert a pressure on all objects that live on the surface of Earth, and this pressure is called the atmospheric pressure. Usually at sea level, atmospheric pressure is equal to 1 atmosphere or 760 millimeters of mercury. Now, as altitude increases, as we go up in space, the column of air decreases, and that's why the amount of gas that is exerting the pressure on this flying object decreases, and that's why the atmospheric pressure decreases. So as you go up in air, let's say you are in a plane, the atmospheric pressure in a plane will be definitely lower than the atmospheric pressure if you are on the surface of Earth. What is vapor pressure? Vapor pressure is an upward pressure which is exerted by vapor molecules as they collide with air molecules above the liquid surface. In the previous slide, we talked about the evaporation process, and I mentioned that those liquid molecules which are at the surface, when they gain enough energy to escape from the liquid surface, they will move into the gas state. Now, once these liquid molecules are in the gas state, those gas molecules will start to exert pressure on the air molecules which exist above them. This pressure, which is exerted by the gas molecules on the air molecules, is called the vapor pressure of a certain liquid. What is the boiling point? Now, as the temperature of a certain liquid increases, the number of molecules, of escaping molecules, will start to increase. Basically, we have more gas molecules now in the space above the liquid surface, and because of this, the vapor pressure, which is the pressure exerted by these gas molecules, will increase. So increasing the temperature will increase the amount of evaporation. This will increase the amount of gas molecules and consequently will increase the vapor pressure of a certain liquid. Now, at a certain temperature T, if this vapor pressure equals the atmospheric pressure, then this temperature T is called the boiling point. So the boiling point can be defined as a temperature at which the vapor pressure equals the atmospheric pressure. So when you start heating a certain liquid, the vapor pressure of this liquid will start to increase. When this vapor pressure equals the atmospheric pressure, this temperature at this moment is called the boiling point of the liquid. What are the factors that affect the boiling point of an organic compound? The first and the most important factor is the strength of the intermolecular forces. As the strength of the intermolecular forces increases, the vapor pressure of the liquid will decrease. The liquid is said to be less volatile and consequently the boiling point increases. Why is that? Because as the strength of these intermolecular forces increases, this means that more energy is needed to break them, and that's why the amount of molecules that can escape from the liquid surface into the gas state will be lower. Why? Because there are stronger forces keeping the liquid molecules together. So, because of this, the vapor pressure of the gas will decrease, and this means that we need higher temperatures in order to be able to force the vapor pressure to increase to equal to the atmospheric pressure. Remember that the boiling point is when the vapor pressure equals the atmospheric pressure. If you already start with a low vapor pressure, let's say for example you started with 0.1 atmosphere as a vapor pressure, this means that you have to heat for a long time in order to be able to reach the value which is 1 atmosphere and to reach the boiling point. Whereas let's say your compound has weak intermolecular forces, which means that your compound has so many gas molecules above the liquid surface, and this means that the vapor pressure of this liquid is high, let's say 0.5 atmosphere. In this case, you need to heat for a less time to be able to reach the 1 atmosphere. And that's why in this case, the boiling point will be low. So to summarize, as the intermolecular forces of your compound, the strength of the intermolecular forces of your compound increases, the vapor pressure of your liquid will decrease, which means that your liquid will be less volatile, and consequently the boiling point of this liquid will be higher. For example, if we compared the boiling points of ethanol and dimethyl ether, we noticed that the boiling point of ethanol is almost like 78 degrees, whereas that of dimethyl ether is minus 24 degrees. Why is that? Because ethanol has the functional group which is OH group, and this OH group is known to form something which is called hydrogen bonding, which is one of the strongest type of intermolecular forces. That's why the boiling point is high. Dimethyl ether, which is CH3O, CH3, doesn't have this OH group, so there is no hydrogen bonding, and that's why because of the lack of these strong intermolecular forces, the boiling point of dimethyl ether will be very low. Now, in compounds which have similar types of intermolecular forces, the molecular weight or the number of carbons in the compound has an effect on the boiling point. As the molecular weight of the compound increases, the boiling point increases. For example, if I compare the boiling point of ethanol to methanol, we notice that ethanol has a higher boiling point. Why is that? Because ethanol has two carbons, whereas methanol has only one carbon. Both of them have OH groups, so they both of them have hydrogen bonds as intermolecular forces. However, since we have more carbons in more carbons in ethanol compared to methanol, the boiling point will be higher because we have a larger compound, we have a larger surface area, and as the larger surface area of the molecule increases, the boiling point will increase. This is another example which compares the boiling point of butane, 4 carbons, to pentane to hexane. As you can see here, butane has 0 degrees boiling point, pentane 36, whereas hexane has 69 degrees. So in general, as the molecular weight or the number of carbons of a compound increases, the boiling point of this compound will also increase because we have a large surface area. This large surface area between the molecules, we will have more contact here, which means that you need more energy to separate these two molecules and move them from the liquid state into the gas state. Whereas if the molecule is smaller, the surface area will be smaller, which means that you need less energy to separate the molecules. So this is the second factor which affect the boiling point of a compound. The third factor is branching. If you have a couple of compounds which have the same type of intermolecular forces and the same number of carbons, but they have different numbers of branches, then branching is expected or is well known to decrease the boiling point of the compound. For example, if we compare the boiling point of pentane, isopentane, and neopentane, all of them have 5 carbons, but pentane has no branches, isopentane has 1, neopentane has 2. Branching is well known to decrease the surface area of the molecule, so the molecule will be smaller in size. And again, because it's smaller in size, the contact with the other similar molecule will be smaller. This means that you need less energy to evaporate this molecule, and that's why the boiling point will be lower. So these are the three main factors which affect the boiling point of a compound. Now, what is the effect of the presence of impurities in boiling point? If these impurities were insoluble, then they are not going to affect the boiling point. So let's say, for example, you added a solid compound to a liquid, and this solid compound didn't dissolve in the liquid. This solid compound will not have an effect at the boiling point of the compound. If the solid impurities were soluble, then the vapor pressure of the liquid will decrease, and because of this, the boiling point will increase. This is called boiling point elevation. So insoluble compounds, no effect. Soluble compounds will increase the boiling point of a liquid. What if we have a mixture of two liquids? If we have a mixture of two liquids, so if two liquids are completely miscible together, then the partial pressure of each component of these two liquids will depend on the vapor pressure of the component and the relative amount of the component in the mixture. This is basically summarized by something which is called Raoult's law. So the pressure of A in this mixture depends on the pressure of pure A times XA, where XA is called the mole fraction. It's actually equal to the number of moles of A divided by the total number of moles found in the whole mixture. And the pressure of compound B equals to the pressure of pure B times the mole fraction of B, which is the number of moles, again, of B divided by the total number of moles. So to summarize, what I'm saying is that whenever you mix two liquids together, then the pressure of these two liquids will affect the pressure each other, and this will in turn affect the boiling point of the whole mixture. The boiling point of the solution will lie between the boiling point of pure A and pure B, and the vapor above a mixture is usually enriched with the compound with the lower boiling point. So the compound with lower boiling point will exist in higher amount here in the vapor state, whereas the compound with lower uh, vapor pressure or higher boiling point will exist with smaller amount that is in here.